Now in a previous video we saw that if a line does not pass through the origin of the z-plane, then under the inversion mapping it is mapped to a circle that does pass through the origin of the w-plane. Suppose we want the image of a circle that passes through the origin under the inversion mapping. Well, we could just take the inverse of this mapping, because the inverse of this mapping is also an inversion mapping. Just swap w and z here. So to go back the way from this circle to this line, we just have to invert the complex numbers on it. So we've just shown that fact now, just using the fact that the inverse of an inversion mapping is another inversion mapping. What about circles that do not pass through the origin? Well, I won't go through that in this video, but I will say that this line here is mistaken. It says here that a circle in the z-plane which does not pass through the origin maps to a circle in the w-plane which does pass through the origin. Well, that's not correct, so we just ignore that. I might not do the inversion of a general circle, but if you want to get a rough idea of the images of various functions under this inversion, you could go to this link here and just draw a rough sketch of a circle. You can see its image under an inversion mapping is not a circle passing through the origin. Actually, it makes sense that the image of a circle that does not pass through the origin is an object, well, it looks like it's a circle that does not pass through the origin. Because if we invert any of the complex numbers on this circle, we are certainly not going to get 0. Here is a rough sketch of a circle close to the origin. You can see that its image is further away, and the closer we get to the origin, the bigger the image gets, as you can see. So that makes sense if we are inverting numbers that are close to 0. If we take a circle centered on the origin, its image will be a circle centered at the origin. The inversion mapping is an example of a bilinear transformation. Now we want A, B, C and D to be constants, such that AD minus BC is not equal to 0. That's just another way of saying that one of these linear expressions is not a multiple of the other one. Suppose AD minus BC is equal to 0. Well, that means AD is equal to BC. Now if we multiply the denominator by AB, we get this here. Now we could replace AD down here with BC. So here we get B squared C. And then we could take BC out of the denominator, and you see that the denominator is just a multiple of AZ plus B. So our bilinear transformation just becomes the constant 1 over BC, and that's not what we want. We can set A equal to 0 and say B equal to 1. Then if C is 1 and D is 1, then we have our inversion mapping, just 1 over Z. Suppose we want a bilinear transformation that maps the complex number z equals 2 to the complex number 1. Well, we just plug 2 in for z and we have to get out w equals 1. So we get this equation here. So we can use any values a, b, c and d to satisfy this equation. But also, of course, we have to avoid the constant mapping, so we need this condition. Here's a similar example, z equals minus 1, w equals 3, so same as before, we just plug minus 1 in for z and set w equal to 3. Next we are going to get a bilinear transformation that sends 2 to 1, minus 1 to 3 and 0 to minus 5. Well, we've already got mappings that take care of a and b. Now we want a mapping that sends 0 to minus 5. So if we plug 0 in here, we just get b over d equals minus 5. Okay, so rearrange this, plug minus 5d in for b up here, and we get 2a minus 5d minus 2c minus 1d. That gives us 2a minus 2c minus 6d equals 0. And in the second equation, plug minus 5d in for b, and we get minus 5 minus 3 is minus 8d on the left hand side, plus 3c bring over the minus 3c, then minus a. Now it looks like we have two equations and three unknowns, so it looks like we will have more than one possible bilinear transformation. Actually, it turns out there's only one such bilinear transformation. Let's eliminate a between these, so we multiply all this equation by 2. So we get minus 2a plus 2a is 0. We get 6 minus 2 is 4c. So we get a 4c, and we've minus 16 minus 6, minus 22. So 4c equals 22d. And from that we get 2c equals 11d. Now if we eliminate c between these two equations, we'll end up with the equation 2a equals 17d. So obviously there's an infinite set of values a, b, c, and a, c, and d that satisfies these equations, but when we plug in here, the d's will actually cancel out. So leaving it in this form here, we can write 2a here, and that's 17d. And if we have 2b here, well, that's minus 10d. And underneath we have 2cz, that's 11d. And then we have a 2d, so the d's will all cancel out. So this will give us the transformation az plus b over cz plus d. That's the form of a bilinear transformation.